is like to study infinitesimal properties of the moduli schemes A, G, N, and I recall for you that AGDN is the moduli space of polarized, so it classifies triples A over S. Is it better? Thank you. Now, So I'm going to write down some formal definitions, and they are going to be boring. But unfortunately, one has to do the definitions. So I'll do, for instance, if I give myself A0 over K is an abelian variety, and then we'll have, we can define a deformation functor, which is, so to speak, the deformations of A0. And there are two ways to define of how to do it, whether defining it arbitrarily or restrict to characteristic 0, characteristic P. So here, what it does is that if you have an Artinian WK algebra, and then this will attach to it the set, the following set. It's the set of isomorphism classes of abelian schemes over R, and plus an isomorphism from a tensored over the residue field. So this is the closed fiber of this abelian scheme. I want to fix an isomorphism of this with the given one, and then modulo isomorphism. Okay, so that's a functor from that category of our Artinian local algebra to the category of sets, and so it's a small black box that this is representable, which will actually prove modulo another black box, and it's smooth, and it's isomorphic to the formal spectrum of over the Witt vectors in a number of variables. And that number of variables is the relative dimension over the ring of Witt vectors. How many variables? The number variable is G squared, where G is the dimension of this abelian variety. And then similarly, we can look at a subfunctor of the deformation functor by restricting to the category of Artinian K algebras rather than WK algebras. And this is representable, and it's again, so this follows from the previous statement. G squared. Okay. Now, next I'm going to define, again, so please bear with me. This seems rather formal. And similarly, so the proofs, yes. Well, not formal, certainly not formal. Well, it becomes formal modulo your theorem. We can have, if we have a polarized abelian variety, so A0 is an abelian variety, and lambda 0 is a polarization on the abelian variety, and then we can define the deformation functor similarly, but carrying a polarization with it. So we'll be thinking about polarized abelian variety, polarized abelian schemes over Artinian local algebras, plus a rigidification at the closed fiber. Okay. And yes? No, but I'm sorry. I think what you are asking, yes, so this is spec of K and spec of R mod, maximum ideal. Thank you. Spec, I'm sorry. R modulo. Thank you. Now, if So following the notation in Francis' lecture, if x0 is a p-divisible group, then just as before, we can think about the deformation functor of an arbitrary p-divisible group. And we can also look at purely characteristic K deformation. And again, modulo black boxes, we'll see that this is smooth if it is over the bit vectors. And how many variables? The number of variables is C times D, where C, D are in the last lecture, where D is the dimension of x0, and C is defined by saying that its sum with D is equal to the height of x0. Okay, and we can have, if we have a polarization, or sometimes some people call quasi-polarization, it's an isogeny from x0 to its dual, then we can consider its deformation, and so on. Okay, they are all representable, but so in general, so they may not be smooth if you have arbitrary polarization, which we will see. Now, let's see, let me keep it here. Now, there are several things I want to do in this lecture. One is, or these are the more boring part. We have gotten them out of the way. Now, it's not clear what to do with this. So what should I do with this? Or it's batteries.
Sorry.
No problem. So I just tried. Hidden varieties, and there is a very close relation between these. That's one of the reasons why we are interested in Abelian varieties and Bersati-Tate group. So one of them is a Serre Tate theorem. The volume down. There are two things in this talk that will be attributed to Serre Tate. And the first one I'll label as Serre Tate theorem. This is in the notes. And what it says roughly is that deforming an abelian variety, let's say A0, is the same as deforming its related, the Bersati-Tate group attached to it. Okay. So let me try to make the statement precise, i.e., so we have these deformation functors. We have A0 over WK as before. Now, if we have any deformation of a abelian variety, that is in a abelian scheme over certain Artinian local ring, then, and a rigidification at the closed fiber, then we can look at the attached p-divisible group. So then if we have A over R, then we can attach to it the p-divisible group over R. So what happens then is that we have a morphism, a map between from this functor, from this deformation functor to the deformation functor of this, the attached Serre Tate group, and the Serre Tate theorem says that this is an isomorphism. Sorry? Stay away from this. This means the right side. So the metal part, I see, that's what caused the problem. So that's that. There is another Serre Tate theorem, which is Serre Tate local coordinates. Okay. And this we'll spend some time on. But before I go into either of these, let me make several remarks. The first remark is, so why are we interested in, so all these deformation functors, there looks like a pretty wild bunch. So the reason is as follows. So suppose we are thinking about studying infinitesimal properties of the moduli space. Now here, I suppose I have a point, a closed point in it. So more precisely, let's say I consider this moduli scheme over WK, and I suppose that I have a point represented by an abelian variety, A0 over K, with a polarization of degree D, and a level n structure, and that defines for me a point, a K point of this moduli scheme, and therefore, this being a point, we can consider the formal completion of this point. This is Grothendieck's notation for a formal completion. So this is the formal spectrum of the completion of the local ring of this scheme at x0. Okay. Now, what is it? If we think about the definition, so this I'll leave as an exercise, which I assure you can do in a few minutes. And that is, what is it? It's the deformation functor that we have talked about over the bit vectors. That's just that. And therefore, if we are interested in studying the local infinitesimal properties of this scheme, it's the same as studying these deformation properties. Okay? So that's the first thing. Now, the second thing is that what are the by the way, so since we have stated Serre Tate theorem, and so we can say that this is the canonical arrow. This is the same as deforming the p-divisible group together with its principal polarization and over the vectors. So one reason for studying the p-divisible groups is that they give us a very usable way to localize, to a method of localization, so to speak, when we want to study properties which are infinitesimal. Okay. So that's that. And of course, another remark is that, so this is related but not that much closely related, is that this deformation functor, so there is a map from deforming an abelian variety together with a polarization. Now whenever you have such a deformation, you can forget about the deformed polarization and just looking at the underlying deformation of the abelian variety. Okay. And it's a fact that requires one can say that it's an exercise. It's an exercise, again, modulo some black box to be stated, that this is a closed embedding. It's not completely obvious. There is a natural error, but the fact that this is an embedding is so this is an exercise. Okay. And there's a similar statement if we replace abelian varieties by Serre-Tate groups. So polarized abelian varieties replaced by polarized p-divisible group, and it's the same thing. Okay, so that's one. Oh, I should let it stay here. Getting away from the metal. Okay. Do I have anything here? Okay. The second thing, the second remark, is symmetry. Local symmetry. Okay. So maybe I should start by looking at the visible local symmetry at this stage. Okay. What do I mean by that? So if I have, let's say I look at the deformation of a polarized abelian variety, okay. Either over K or a mixed characteristic. Okay. So what I mean is that we, at this stage, or here, we have deformation of an abelian variety. Okay. We know that, so for instance, we know that the bigger one is represented by a smooth formal local scheme. Here, this is smooth if lambda 0 is principal. So in some sense, we think we understand these underlying spaces. These are formal schemes, the formal spectrum of a formal power series ring. But I would like to say that we don't actually understand them. And the reason is the following. In either of these situations, in general, there is a symmetry group. What's the symmetry group? Let me first say what the symmetry group is. Here we have a natural action of the group of automorphisms of this abelian variety. Okay. Why? If you think about the definition, I have for every Artinian local algebra R, where I'm thinking of pairs of the form A, and then this is a spec R mod MR to A0 base changed to spec R. Right? Now, the point is that if I have automorphism of A0, then I can compose it and produce another rigidification. So if I have gamma in here, then by composing, or post-composing with gamma, I get another one. So this operates functorially, and therefore what that means is that I have a natural 100% canonical action of this group on this deformation space. Okay. How large is such a group? Well, we often hear that the automorphism group of an abelian varieties are finite. That's not correct. So they can be infinite. Now, should I give an example? So if I take A, an abelian variety, I'll take A to be, let's say, G copies of an elliptic curve. Okay? So elliptic curve, by that I mean one-dimensional abelian variety. So let me just exhibit lots of automorphisms. Okay? Why? Because now I know that n by n, G by G matrices with coefficients in Z, of course, operates on this product in a natural way. So let's say A0. Now, what's automorphism? Automorphisms are the group of units of anamorphisms. This is automorphism of A0. And what is this? This is your favorite group. And if G is not 1, I claim that this is a theorem that is infinite. Okay. So we have this action in general. Okay. Of course, there are some abelian varieties. I mean, this may well be plus minus 1. But in principle, they can be large. Okay. Now, similarly, we have the group of automorphisms of A0 lambda 0 operating on it. Now, this time, it's correct to say that this automorphism group is finite. And that's something you can read in standard books. For instance, Mumford's group on the abelian variety. So this is a finite group. On the other hand, just knowing that this is a finite group doesn't mean that this action is trivial. And I'll invite you to do as an exercise to figure out what happens. So if you have a non-trivial finite group of automorphisms, what the action would be. It's not easy. Now, but I say, the next remark I'm going to make is that, in fact, so these are just, the group looks not too big. This looks discrete. But in fact, it's a lot bigger. There's a lot bigger group of automorphisms operating on it. It's just that in this way, we don't see it. Okay. Now, how do we see a bigger automorphism group acting on these moduli spaces, on these local deformation spaces? Well, we remember, for instance, this is canonically isomorphic via this arrow, this direction, to the deformation functor of the polarized p-divisible formal group attached to this polarized, oh, sorry, here, this is no polarization. They're the same. But after we realize this way, then we see that there is an action by not just the group of automorphisms of this abelian variety, but rather, by the same formal argument, the group of automorphisms of the p-divisible group attached to it. Now, how large is this? So let's assume that K is the algebraic closure of it. Now, how large is it? Well, let's say, let's even look at, so I'm getting ahead of myself. Maybe I should go over here. Now, suppose, let's say, in the simplest situation, even the simplest situation. Now, and we'll talk about, so simplest, by that I mean the case when the dimension of the abelian variety is 1. Okay? It's hard to be simpler than that. Now, as you heard that in Francis' talk, that not all one-dimensional abelian varieties in characteristic P are the same. Infinitesimally, they look different. This is one of the features of geometry in characteristic P. So let's do some examples. So the one example, I'll start with the harder one. So A0, and suppose that is supersingular. So A, let's say E0. So dimension is 1. So I change from A to E. So elliptic curve. We haven't defined it so far. We will more generally, but so at this stage, it just means that it's not ordinary. While ordinary was defined in Francis' lecture. So not ordinary. Okay. Now, again, here I'll tell you a fact which we'll do tomorrow. So in this case, what is the group of automorphisms? Maybe I'll start with endomorphisms of the Bersati-Tate group. So easier. Of the p-divisible group attached to it. This is a fact we will do. So it's a small black box. That this is a quaternion quaternion central division algebra over QP. Okay. And there is up to isomorphism, there is only one such. So it's dimension. I'm sorry, this is not the quaternion, it's maximal order. The maximal order in the central quaternion division algebra over it. Okay. And so now automorphism group, so I call this O of D, where D is this division algebra, so that the automorphism group is just the group of units of this maximal order. It's quite a large group. It's a p-adic group. And so we know that the deformation functor of E0, which is the same, WK, is the same as the deformation functor of its Bersati-Tate group, p-divisible group. And we have this pretty large p-divisible. This is a, what is this? This is a compact p-adic group. What's its dimension? Well, the tangent space is the underlying vector space of that. So dimension of that p-adic group is 4. It's a 4-dimensional group operating on it. Okay. Now, so this it's not the hardest case, but I claim that, well, certainly I don't really understand this action at all. I don't. Now, so if anyone's interested, this is some exercise one can sort of play with for at least a whole day. Now, in the contrary, the case A, the easier case, if that is A, is ordinary. Okay, so here it's I'll take this opportunity to supplement, so the last lecture, with 2 more definitions of ordinary abelian varieties over a field of characteristic P. So more, so aside, A0 over K is ordinary. We saw several definitions, properties that characterizes this, and there is an equivalent definition. There are many more that one can use, but I use one that's strong, which says that if we look at its p-divisible group attached to it, then first of all there is a maximal état quotient. So I could, let's say E. So this is état. Let me write it this way. So K is algebraically closed. And characteristic 0, so I say this is constant. That's easier. And here, this is the p-divisible group attached to a torus. So, and then for how many copies? G copies, G being the dimension, and this is height equals G. So in other words, for here I'm saying that there is an equivalent definition of ordinary abelian varieties. Sorry? Height of E. I'm sorry. So this is one definition of that. Okay? Because we will need that later. Now, in this case, quite in contrary to the previous situation, I claim that in this situation, we can completely understand the action of this automorphism group on the deformation space. And so the general statement, this is a special case of the Serre Tate local coordinates for ordinary abelian varieties. Okay. Let me first tell you what happens in this situation. So in this situation, so the deformation of E over the bit vectors is, as we said, that K, this little k over there, the deformation of EP infinity over WK. So I'm stating some facts which I'll try to indicate how to prove. So this is isomorphic to a one-dimensional formal torus over the bit vectors. Okay, so that's easy enough. Now second, what is the automorphism group of this Serre Tate group, of this p-divisible group? What's the shape of it? Okay. Well, this being over a perfect field, or in fact algebraically closed field, one can check that this short exact sequence actually has a canonical splitting. Okay. So it's a product. Okay. Now, there is no non-trivial homomorphism in between mu and constant ones. So if you grant that, then the endomorphisms of a product is the endomorphism of the connected of the mu and the endomorphism of this constant. Okay? Now each one has dimension 1, has height 1. Now this I can, okay, here. So I can say this is an exercise, this is something after what I said, this can be done. It's a copy, so it's two copies of this. Okay, ZP cross ZP. Right? Now, the next question is, what's the action? So we know that there is an action of this p-adic group. This is a compact p-adic group. We think we understand this group. It's that the local units. We also understand this group. That's the formal torus. To have an action means that we have a homomorphism from this group to the group of automorphisms of this formal torus. What is the group of automorphism of this formal torus over the bit vectors? That, again, I'll leave to you as an exercise, and that is canonically isomorphic to ZP cross. In other words, the automorphism you can have is raising to some power. The power has to be a p-adic unit. Otherwise, it's not an automorphism. So we know that we have a natural map with homomorphism from ZP, for two copies of ZP cross to ZP cross. And I'll state a theorem, state a fact, which we should be able to deduce from the Serre Tate local coordinates. And what is it? What's the map from here to here? Well, if you have lambda 1, lambda 2, it depends on sort of the ordering with this isomorphism. But what this map is that this goes to lambda 1 inverse lambda 2. That's this map. K is an algebraically closed field. So that we have the automorphism is maximized. Well, but in fact, you have this whenever you have a perfect field, because the automorphism is defined already over a perfect field. So we have this. So this is a general phenomenon that we can, in the case, that's that. In the case that we have the abelian variety is ordinary, or the p-divisible group is ordinary, we can completely understand the action of the local automorphism group by And the action is, in a strict sense, linearized. It's completely linearized so that we can understand them by linear algebra. Better hurry. Oh, but there's another remark. It's a crucial remark that I would like to make here. That these, for some reasons, or these automorphisms, these actions, were not emphasized in the literature, perhaps because people didn't look at them carefully. Although in a paper by Lupin and Tate, they actually did it in a special case. Now, for these lectures, there's a genuine reason that we are interested in these automorphisms. And the reason is this. So one of the things we study in these talks is Hecke orbits. Okay? But in fact, so if we think about this, so the real objective is not understanding these orbits. Every orbit, so a priori, is a finite set. The Hecke orbit is really the one that we really are interested in is the study of Hecke symmetry. So for instance, on AG, let's say 1n. Okay? And I think in Henri Damon's lecture, so you have all heard that, so at least when G, in the case that G equals 1, so the modular curve has lots of algebraic correspondences on it. They're called Hecke correspondences. And similarly here. So there is a large automorphism, or not automorphism, but Hecke algebraic correspondences. So this is one of the standard phenomena. Or if you haven't seen it before, if this is the first time you see it, it sounds like magic. What happens is that if you vary the n, then you get a tower of modular varieties as you vary n. And so the maps are Galois covers. So a priori, you get a group which is a Galois group of these covers operating on this tower. The Galois groups are profinite groups. In particular, they are compact. But in fact, there is a much larger group operating on it, which is the symplectic group, but with values in finite adels, prime to p finite adels. So this is the notion for prime to p finite adels, which is, if you like, this is a restricted product of QL, so L not equal to p. And so this group action, so when reflected at a finite level, becomes the Hecke correspondences. So one of the objectives is to study these global symmetries. Now, so in mathematics, we always try to sort of use calculus, try to reduce everything to calculus in some sense. So in other words, we would like to localize and try to localize, so whenever we can, to study sort of these symmetries. And we localize, when we localized the symmetries, they actually becomes, well, in a certain sense, not all of it, but this action of the automorphism group of A0 lambda 0 p infinity on the deformation space. So that's the real reason that we are interested in. And so what I was saying was that in the case of ordinary situation, we can completely understand it. We can completely understand the action. And in some sense, although I'm not formulating it as a mathematical theorem, that the case that the abelian variety is ordinary is the only case that that this action can be completely understood by linear algebra. Now, so I have a little over 15 minutes to explain the rest. So the first thing I would like to say, I think I have already stated the Serre Tate theorem as a black box. But fortunately for me, I think in tomorrow's lecture by Professor Messing, he will explain how to prove this theorem. And since I'm running out of time, I will only say very briefly about the technique used in the proof. And by the way, so I think the first published proof of Serre Tate theorem appeared in Bill Messing's thesis. So remarks about tools for studying these deformation spaces. And what that is the Grothendieck-Messing. So that's one, the general method. The Grothendieck-Messing method of attaching sort of crystals attached to p-divisible groups. Okay. And the more precise statements are in the notes, although they're about, so let me say, so you have input data is what's called so PD structure, divided power structure. You can see the notes for precise definition. What that means, roughly speaking, is that for I is an ideal, R is a ring in which P is locally nilpotent, and then we have lots of maps called gamma i's, and these are, in some sense, gamma i's are intended to be so raising x to the n over I to the n factorial, but this x to the I, and trying to, there's a set of properties to make sense out of it, and we want it to be nilpotent, that in the sense that for every x in I, so some power, so then so if your I is large enough, then it becomes 0. This is slightly different and more general than what I wrote in the notes. And whenever we have these, and we have p-divisible group x0 over R mod I, then you have miracle. It's almost, if you haven't seen it before, it's like magic. So what this means, among other things, is that you have, in some sense, a crystalline first cohomology group. And so in the notes, I wrote some D, it's a duodonate crystal. But in some sense, it's x0, but evaluated over R. So without actually having to lift these p-divisible group, you already have a linear algebra data that's there. But moreover, you have H1 over this, H1 x0 over R mod I, which happens to be canonically isomorphic to H1 of x0 R, reduced mod I. Over here, there is a Hodge filtration. Okay. And then the theorem, which you can read the details in the notes, says that lifting, whenever we have such an input data, and if we try to lift a p-divisible group defined over R mod I, lifting from here to R is the same as lifting this Hodge filtration. So in that sense, whenever you have such an input data, a nilpotent divided power structure on this extension, you can understand at least one step. So when you only try to deform it one step out by linear algebra. Okay. And one, I should say, what makes it good for, at least for standard deformation theory, is that when I square is 0, then we can have a trivial PD structure, or DP structure. So, but I square, so how does one do it? It's that for all the gamma i's, for I bigger than or equal to 2, you just define them to be 0. And if I square is 0, that's a well-defined divided power structure, and but I square equals 0 is the standard form, is in quote-unquote standard deformation theory. That's so to speak the standard deformation, standard input data. Therefore, if we are only interested in deforming over square 0 extensions, we can completely understand everything by linear algebra. Okay. And with these, if you look at the notes for the precise statements, it's possible to deduce the smoothness and representability of the deformation functors as exercises. So that's a pretty big black box, which I'm sure you will hear more in today's and tomorrow's lecture by Bill Massey. Okay. So now I have about 10 minutes to do the Serre Tate local coordinates. Let me try to do that. And I hope to be able to prove something. So, let me first tell you the precise statement of the Serre Tate local coordinates. Okay. So here, suppose that x0 is a ordinary p-divisible group. Let me just, for simplicity, I'll just do it over an algebraically closed field. Of characteristic P. What that means is that I have a canonical so for every group, every Serre-Tate group, there is a maximal eta quotient. Over algebraically closed field, eta means constant. Okay. And how many copies are there? There are, this is C. Okay. So the number of copies. And then there are D copies of it. Okay. So canonically, I'll say that this is the maximal eta quotient, and this is the maximal multiplicative part of the Serre-Tate group. Now, if we look at the deformation space, so if you have any deformation over R, it's a fact which one can do by using the fact, so this is usually called rigidity, which means nothing but that when you deform an eta thing, or lifting an eta thing, then you have, for instance, if you have an eta group scheme, or eta p-divisible group, and then you can just lift it whenever you have an eta, whenever you have a nilpotent extension. There's a unique lifting. So whenever you have a lifting, or deformation of x0, then again, we have this defined over R. So this is base change to R. And here we have mu p to infinity over R. We have this. So in other words, so this is given. So whenever you deform it, it's given. You have this natural exact sequence. Okay. So in order to determine this deformation, the only data that encodes it is how this p-divisible group over R is fitted together from this constant one by this multiplicative one. Okay. So the theorem says, so let me theorem, this Serre Tate coordinates. Serre Tate coordinates. So suppose sort of the assumptions as before. So if we take the deformations of x0, let's say over arbitrary thing, we would like to understand it. And the theorem says that we have a canonical isomorphism from, let me say Tp of x a tau, 0 a tau. So it's this thing. And going to what I'll say, x0 hat. So this is the formal group attached to this. So in some sense, you're taking the formal completion of this Serre-Tate group. So this, I remind you, in this situation, this is QP mod ZP, and this is GM. So this is C copies, and this is GM hat D copies. Okay. And this is the sheafified harms over ZP. Okay. And what this is that this is just a canonical way of writing that this is isomorphic to a number of the formal torus. How many copies? It's the rank, the product of these two, because each one, so this can be deciphered by, yeah, this is obvious. Okay. So this is the statement. Sorry? TP is the Tate module attached to this A-top Serre-Tate group. So A-top Serre-Tate group can be understood, let's say, by the Gallo action. Since we are sort of thinking about over an algebraically closed field, the Gallo action is trivial, so there's nothing. Okay. So I tried, my intention is to try to at least indicate a proof to you in 3 minutes. Okay. Now, so the general way of proving such a statement is that once you have this canonical isomorphism, we have a canonical map. There is a canonical map over here. So once you have a canonical map, you only have to check that this is an isomorphism. And because this is a canonical map, and these are product structures, so you can easily reduce it. So this thing by standard algebra, you reduce it to the case that C is 1 and D is 1. Okay. So the proof is descent, plus reduction. It suffices to show, to prove this in the case that C is D equals 1. Okay. And then x0 is mu p infinity plus qp mod zp. That's the only one one has to consider. And so as we explained, so if we are over R, R is an Artinian local algebra over the bit vectors. So we need to compute the ways we can extend, the isomorphism classes of extensions. But extension has to reduce to the given one in general. So what's the isomorphism classes of all extensions? First, forget about the condition that when you reduce the closed fiber is the given one. Well, that is, we'll just look at extensions. Mu p infinity. Now this, by an easy argument, you can convince yourself that this is the limit of extensions. If I look at this Serre-Tate group, or this p-divisible group, so each time I can look at what happens if I just look at its p to the n kernel. If I look at its p to the n kernel, we see that it's an extension. what it is an extension of, it's an extension of p to the minus n z over z by mu p to the n. So, this is over R. Right? Now, how do we compute this? This can be easily computed by Kummer theory. How do we do that? I'll recall for you what Kummer theory is. Kummer theory is Gn 0 or 1 for mu p to the n. 1, this is p to the n. Right? And so we do that, and what Kummer theory tells us is that this is isomorphic to R cross divided by R cross raised to the power p to the n. That's the standard Kummer theory, just using exact sequence from it. Okay. Now, there's a slight difference of this. Now, we're using the fact that the residue field is perfect. Okay. That being perfect, this quotient is canonically iso, and then take the limit as n goes to infinity. Now, on the individual level, that is, I claim that this is isomorphic to using the similar quotient, but with principal units. Okay. Because when you look at the map going to k, so raising to p to the n is surjective. Okay. So this is because perfect. Okay. Now we take this, so you have to convince ourselves how to take the limit as n goes to infinity. And so you think about what that means. You see that this is just 1 plus m to the r. Because this is Artinian, so when you take, and p is less. So, now, lastly, so I think I apologize for going over for maybe 2 minutes more, but I would like to state a theorem. Let me go over this. Which, at this stage, looks rather unmotivated. But it'll be an ingredient we need later, and this seems to be the best time to state this theorem. Okay. So innocuously, this is a very elementary theorem, elementary in both the statement and the proof. Okay. So let's say, I'll say that X is a formal torus over, say, algebraically closed field, characteristic P. So this is, what that means is that it's isomorphic to some copies. Okay. Now, I suppose that I have a reductive group, so this is stated this is written down in the notes, reductive group over QP. And I have, in this case, a homomorphism from this to GL of capital N QP. Okay. So I have an open subgroup that goes to GLN of ZP. Okay. And therefore, it operates on X. So this is sort of GL of X. So X star, X lower star tensor with QP. Like. So we have an action of U on the formal torus. Right? And so this is a representation. And assume that rho contains no trivial representation as subquotient. This is a reductive algebraic group, so it sort of decomposes into direct sum of irreducible representations. I'm assuming that none of them is trivial. So, and then suppose I have a closed, irreducible subvariety operating, containing this formal torus X. Okay? And assume that it's stable under the action of U. So remark that such things are very easy. So there are lots of examples. The simplest one, perhaps, is to take G to be Gn, GL1. And then, then here you take it to be some open, some subgroup of principal units in ZP, or ZP cross, and operates by homogeneity. That satisfies this condition. So, and stable under U, what's the conclusion? The conclusion is that Z is a formal subtorus. Okay. And why is anyone interested in this? That's because when one localizes the Hecker orbit problem, so this becomes the corresponding localized problem. And such local information will tell us a lot about global information. Thank you, I'll stop.